refining the root locus. In the last class, we have seen the 5 basic rules of plotting the root locus. Sometimes to make a more precise root locus, those rules are not enough. So for this scenario, we have to introduce few more rules that will eventually help us to plot the root locus more efficiently. So first of them is real axis, breakaway, and breaking point. So first additional rules. Okay, so the first one, rule 1, is real axis, breakaway, and breaking point. Okay, so what does it mean actually? So if we want to see here, say we have a transfer function k g of s, h of s equal to k by k into s minus 3 s plus s minus s minus 5 divided by s plus 1 s plus 2. So basically we have 2 poles to 0. So zeros are in the right half plane and the poles are in the left half plane. So somewhere here -1 and -2 we have 2 poles, and at +3 and +5 we have 2 zeros. So by looking at this equation, if you try to plot the root locus, the formula for the real axis segment says that the segment that is left side of the odd number of pole 0 is on the root locus. So based on that formula, basically this portion is on the root locus as well as this one. And since our pole and the 0, finite number of pole and 0 is equal, so basically we can say that there will be no infinite lines because the poles have their corresponding zeros in finite location. We don't have to go to the infinite location. So, but how we are going to, for this case, what should be the pattern of the root locus? So as we know, I think, so for the rule number 4 says that it will always start from pole and it will end to 0. So eventually what it will be is at k equal to 0 is styled like this. One will be moving in this direction, the other will be moving in the opposite direction. So at some point they will merge together, and that point from which they will leave, okay, so they leave the root locus or the real axis, then it will go into somewhere there, and then it will come like this. In general, it is circular fashion, but because of the tab, it doesn't make it circular. So one of them will be going in this direction, and the other one will be going in that direction. Okay, so just for fun, we say that true love always finds its partner, isn't it? So the pole leaving the real axis through the imaginary axis is going to other side to find its corresponding partner. So This point here is called breakaway point, real axis breakaway point. And the point where, through which it is actually entering to the real axis again. Not necessarily always it has to be one breakaway, break-in, but it may happen that one breakaway, then it will merge to some complex pole or zero. So I will show one example of that one as well. So break in point. Is it okay? So this is breakaway and the definition of the breakaway and the breaking point. Now the question is how to figure out the breakaway and the breaking point. So for that, what you can do here is, let's try to bring another plot. Okay, so it's gone downwards. Let us go there. So -1, -2, then +3, +5. So now what we are doing, we are starting from pole, we are going to 0. So starting from pole means at this particular point of the pole, actually, we have 0, starting from actually k equal to 0. So the initial gain will be actually k equal to 0. So, and gradually the value of the k will be increasing. So as you can see in this axis here, say we are just calling this k versus sigma curve. So say this is k, this is sigma. So because we are only interested with the real axis. So now this is just starting point. So at this location, the value of k is actually 0. Same here, at this location, the value of the k is 0. So gradually what will happen if you go closer to your breakaway point, closer, so in this way or in this way. So what will happen, the value of the k will have a pattern like this. So at that breakaway point, the magnitude of the k will be maximum. K will be maximum. So for the only real axis that we are considering. Only in the real axis, if you try to figure out. So for that, what we are doing, we are not taking s equal to sigma plus j omega. We are just taking s equal to, because we are only considering the real axis, only sigma. So in the equation, we just approximate s equal to sigma. That will eventually help us to figure out only in the real axis, which is the point at the point at which actually the value of the k will be maximum. Similarly, this is about your breakaway point. So at the breakaway point, the value of the k should be maximum. Okay, so similarly, in the break-in point, the value of the k, I think you already guessed that it has to be minimum. So the point at which it will actually enter, the point at which it will enter, say it has here, it has, it is happening for say k equal to 25.6, something like this, arbitrarily, we don't know. Okay, so here it is entering. So in the next instant, somewhere here, the value of the k will be higher than that. So basically, you say 30.6 or 56, something like this. So this point actually corresponds to minimum point, and gradually increases, and here it will be becoming k equal to minus infinity. Sorry, k equal to infinity, because we don't consider the negative values of k. Is it okay? So in this case, what we are going to see, we are going to see a curve like this. We may see something like this. Okay? So something like this. So this may be the corresponding minimum value. So we are calling this point as sigma 2. and this is plus because in the right hand plane. So this point here, maybe we call this one as minus sigma 1. Okay, so sigma 1 minus sigma 1 is actually our breakaway point. Breakaway point. And plus sigma 2 in this particular case is actually our breaking point. Breaking point. So bottom line is we have to figure out the maximum and the minimum value of K. So this is K minimum. Okay, so we already know the formula for the K. So the formula for the K is basically K G of S, H of S has to be equal to minus 1, the last class, the fundamental thing. So we can say that the value of K will be minus 1 by G of S, H of S. Now, as we are saying that we are only interested about the real axis, so S will be replaced by sigma. So we are having K equal to minus 1 G of sigma, H of sigma. So what is the next step? This is how we are going to find the equation. So after finding the equation, the next step will be we have to figure out dk by d sigma, and we set it to 0. That will give us the conditions, or basically the locations, sigma 1 and sigma 2. In this case, particular case, actually one positive, one negative. Okay, so let us start with this example that you are seeing here. So this is actually your examples 8.1, example, sorry, 8.3. So K, G of S, H of S is, as we already said, K, S minus 3, S minus 5. Then we have S plus 1, S plus 2. Now we replace S by sigma, so what you are going to get is G sigma, H sigma will be something like this. K sigma minus 3, sigma minus 5. Then you have sigma plus 1, sigma plus 2. So don't get confused, this is not 6, this is sigma. So what you can say, K will be eventually equal to minus, so it will be just altered. So sigma plus 1, sigma plus 2 divided by sigma minus 3 and sigma minus 5. Okay, so just multiply. So after multiplication, what we are going to get is minus sigma square plus 3 sigma plus 2 divided by sigma square minus 8 sigma plus 50. So next step is fairly simple. So you go for dk by d sigma. So basically we'll have something like this. Sigma square minus 8 sigma plus 15 square, then sigma square minus 8 sigma plus 15. I think you already know, but still I'm doing a bit slow. Don't forget the negative sign. Okay, so eventually actually it doesn't make any difference, the negative sign, because of the fact that we are going to make it set it to 0. So negative sign can actually be omitted. It can go into the other side. So then you have 2 sigma. If you differentiate, then plus 3. And then you have minus sigma square plus 3 sigma plus 2 into 2 sigma minus 8. Okay, so go for the calculation. Eventually what you're going to get is sorry, 11. I think you can do the rest of the calculation, so I'm just omitting that part. So 11 sigma square, 11 sigma square minus 26 sigma minus 61 divided by sigma square minus 8 sigma plus 15 whole square. So as we know, this has to be equal to 0. So eventually we are not bothered about the denominator. So only the fact that we are interested about the numerator. So 11 sigma square minus 26 sigma minus 61 equal to 0. So basically sigma 1, 2 minus b, that is 26, plus minus b square, 26 whole square minus 4 into 11 into minus 61. So divide by twice a, so 2 into 11. So this is going to give us minus 1.45 plus 3.8166. Okay, so now if we look at look at our original curve here. So if we try to plot here, so we can figure out this will be actually minus 1.45, and this point here, it will be eventually plus 3.8166. Okay, so we can actually find out the breaking point, and then we can directly add them through a circular fashion. So you can use as a circle. You can find out take this one as a dia, and then draw a circle like this. So that will be your root locus. Now, this calculation using the derivative and set it to 0, then find out the condition. This can be done. In some cases, some alternative formula is also given. This is called transition method, alternative to the differentiation. I think this is dynamic control system by Franklin. From that book, it has been taken. So transition method, similar approach. So because the denominator is not important, so that is why only the numerator calculation is important. So this method is talking about only the calculation of the numerator. So transition method. Transition method. So what it says, that summation of I equal to 1 to m 1 by sigma plus ji zi equal to summation of I equal to 1 to n 1 by sigma plus pi. Okay, so it does look a bit complicated, but idea is very simple, just like the previous example. So we have two pole, 2 0 at plus 3, so sigma minus 3 plus 1 by sigma minus 5. So summation of all the zeros divided by equal to summation of all the sigma plus 1 plus sigma plus 2. So if you now take do the multiplication, what you are going to get is a denominator. You have sigma square minus 8 sigma plus 15. In the numerator you have twice sigma minus 8. Okay, so you're just adding those two values. So similarly, twice sigma plus 3, and this is your sigma square plus 3 sigma plus 2. So if you now compare this equation with the one that we have above, so actually we are just taking this parameter, this parameter, this parameter, and this parameter. So we are just omitting this parameter. So this is an alternative way. But in some cases, I have seen that this doesn't work well in case of your complex pole and zero, unless otherwise you actually take the complex conjugate as well. So you in that case, it is better to go for dk by ds, or sorry, d sigma, than set it to 0. So this works in whatever the condition you are given. So set it to 0. So I think for our case, for safety, even though it takes slightly more time, this is better eventually. So you can go for this method. Okay, so this is the finding the rule number 1, that is breakaway breaking point. And one thing I just missed, always the breakaway breaking point, they will leave at an angle given by 90 degrees. Okay, so they will always leave at an angle 180 degree divided by n, where n is, so general formula is at which angle the breakaway breaking will be taking place is 180 degree divided by n. So where n is actually nothing but the number of poles and zeros involved. So this is always true, always 2. So either 2 pole is merging together, or from 2 pole it is going to the 0. So basically it is always 90 degree. So 180 degree divided by 2. In the real axis this is happening. So it is always 90 degree. So now look at this one here. So that is why it's always better to draw a circle. So as you can see here, this will be 90 degree. Okay, so at 90 degree they will be leaving, at 90 degree they will be entering. So a circle will be perfect shape for drawing this way. Next is next rule is so additional rule that we are learning is j omega axis crossing. So the j omega axis crossing. So actually, if we can figure out whether the curve will be actually crossing the j omega axis or not, it gives us two information. That one information is whether actually our system is becoming at some point stable or unstable or not. So that information can also be extracted from this j omega axis crossing. So like here, I don't know whether you have noticed or not, that curve that we have plotted here, actually we are starting from k equal to 0 here. So k equal to 0 here. For some value of k, it is stable. So this zone, say k equal to here k1. So at k equal to k1, our system is oscillatory. Okay, so oscillation will be there, oscillatory. And k lesser than k1, our system is stable, because all the closed loop poles are actually in the right half plane. That k is lesser than, greater than k1, then our system is becoming unstable. Is it okay? So this information actually we can find if we know whether actually our system is crossing the j omega axis or not. So it is always better to go for the j omega axis crossing. It will help us to figure out whether the system at some point is becoming unstable or not. So for that, we have to take the help of the Raut Hurwitz criterion. So the table of chapter 6, Raut Hurwitz criterion that we have to use. So if you need, you can just have a review of that thing. That method is itself simple. So chapter 6 review. Okay, so say one of the problem that we have seen in the last class is k g of s h of s equal to ks plus 3 s plus 1 s plus 2 s plus 4. So we have 4 pole, 4 pole and 1 0 in that system. We already seen this behavior in the last class. So now we are interested about this one when I'm not sure whether you recall or not. So we actually had something like this. So one of the pole was from 0 to 1. The poles were actually merging together. Then the guiding line was 60 degree and 300 degrees. So they're actually approaching this line and this line. Okay, so now again, as you can see, this system is actually crossing the g omega axis. So actually how to figure out for which condition and which value of k it is crossing the g omega axis, then that will guide us what value, up to what value we can, what value of gain we can provide to the system. So any higher value of gain than that, the system will be in the unstable zone. So let us find out the closed loop transfer function of this one. So closed loop transfer function T, because we have to deal with the characteristic equation. So Ts equal to k g of s 1 plus k g of s h of s. So in this particular case, we don't have to bother about this because actually h of s was 1. So we can simply write that ks plus 3, then we have the whole number of poles, every one of them, s plus 1, s plus 2, s plus 4, divided by 1 plus the whole thing again. So if we simplify, we are going to see that k into s plus 3 will be there, and we'll have s plus 1, s plus 2, s plus 4, then plus k into s plus 3. Okay, so we are not at all bothered about the numerator, so just simplify the denominator. So k s plus 3, then if you just multiply and simplify a bit, then what we are going to get is s to the power 4 plus 7 s cube plus 14 s square. You can actually tell me whether I'm just skipping one or two lines. So if you feel that I should cover every single line, that takes actually a bit of extra time. So if you feel that, still I'll try to cover it, but if it is not making any problem for you, then I can skip one or two lines. That will make things a bit faster. Because I'm wondering, actually, I have to take few extra classes to finish the course, so that those of you who are actually interested to learn, they can actually learn the whole process. And this is online, so I can simply just make the video and give it to you, and you can actually learn. I'm not sure whether you're actually getting benefit or not, but this is the way, I think, best utilized way if you are interested, and because of the fact that in the class, whenever I delivered something, So there is a possibility there that a portion of you are always missing. But here, even if you look at the class, don't look at take notes. In that case, also you have the video with you, and you can see what are the portion that you have missed. Or so I want to be sincere and honest in teaching you, and in the likewise, if you are sincere and honest, then actually you can take full advantage of it. So I don't want to cover anything in a hurry. So just let me know. So this is our characteristic equation, and the highest order is 4. So Rauther-Ritz table that we are going to form is s to the power 3, is s to the power 4, s to the power 3, s square, s to the power 1, s to the power 0. Okay, so let us fill up the table. So what we have is the first one is 1. I think you already recall that we follow this zigzag pattern. So 1, 7, then 14, then 8 plus k, then you have 3k, and the rest of them is replaced by 0. So the first one, and then we follow forming 8 pattern like this, multiplying this and divide by this. So it will be eventually 7 into 14 minus 8 minus k divided by 7 again. So it will be 98 minus 8 minus k by 7. So eventually what we are going to get is 90 minus k by 7. So here this is 90 minus k by 7. And you have, since we don't have any parameter here, so it will be 3k. Okay, so for simplicity, both of these can be multiplied with 7. So you can omit this parameter and it will be actually 21k. Okay, so in the same row, we can, if you can recall, the same row we can actually multiply and divide with some common factor. Okay, so next is, so now if you figure out what will be the next value, so it will be 90k. So for the next value, what we are going to have is, again from the 8. So from the 8 will give you something like this. So 90 minus k into 8 plus k minus 7 into 21k divided by 90 minus k. Okay, so if we simplify it, we just multiply and simplify, then what you are going to get is minus k square minus 65k plus 720 by 90 minus k. Okay, so put it here, minus k square minus 65k minus plus 720 divided by 90 minus k. And this value is definitely is going to be 0, and this one will be coming here 21k. Now for finding the j omega axis crossing, we know that the entire row has to be 0. So this one cannot be. Okay, so we can actually take, and also it is difficult to make this 1 0 as well, because of the fact that 21k is 0. So If for this one to make 0, you have to make k equal to 0. But if you take k equal to 0, this column will this one will not be 0. So that is why only possible thing is for us is this one. So what you have to do is basically, if you make this one equal to 0, then what we are going to get is minus k square minus 65k plus 720 is going to be 0. So let us find out the value of the k, for which the value will be 0. So minus b, that is 65, plus minus b square put over 6 minus 65 square. So 65 square minus 4 into a is minus 1 into 70. So the under the root over it is becoming plus, so you don't have to bother about it. 2 into minus 1. So what we are going to get is 65 plus minus root over 7105 divided by minus 2, and then actually 65 plus minus 84.291 divided by minus 2. Now this gives us two values. One value of k is minus 74.6455 and the other value is 9.6454. So as we say that the value of the k for our analysis is always greater than 0. So basically we have to take k equal to 9.6455. So the row in which we are making all of them, all the rows 0, then we have to take the equation before that. So that is basically 90 minus k s square plus 21 k equal to 0. Because as you know, the first one is the power of s square, omitting the 1, the second one is the power of the s0. So s0 is nothing but 1. So what we are going to get here is 90 minus 9.6455 whole s square into s square plus 21 into 9.6455 equal to 0. So basically it will be 80.35 s square plus 202.65 equal to 0. So this will give you two values of s. So basically s square will be minus 202.65 divided by 80.35 is equal to minus 2.522. So s will be basically 1, 2 will be plus minus j root over that value. So eventually 1.588. So we can easily figure out the location through which actually the plot is going to the j omega axis. So if you want to refine the equation that we have seen, the plot that we have seen in the last class, then you can actually figure out the point through which will be an additional point we can figure out, and the corresponding magnitude of the k is also known. So we can actually have more points, and then we can gradually approach the asymptotes. And also we know that this will be leaving at an angle of 90 degrees. So initially it will be 90 degrees, and gradually through this point, then it will be going to asymptotes. So this is your additional rule number 2, that is finding out the j omega axis crossing. Now next is third rule. Third rule is actually angle of departure and angle of arrival. So rule 3, angle of departure and angle of arrival. Yeah, it seems like departure and arrival, going to somewhere, leaving somewhere. So this also will help us to actually find out the guiding how from a particular, and these are actually related to your complex. So these two are related to complex pole and zero. Okay, so complex pole and zero. Sorry about this. Sometimes the stylus doesn't work as it should. So these are related to complex poles and zeros. What does it mean actually? Let us go to the intuition first, then we'll. So we have a pole here, we have a pole here, or maybe we have a zero here, we have a zero here. You can have also pole here, zero here. Okay. So we know that this segment here is on the root locus. Okay. So this segment is on the root locus. So and direction of this one will be on, something like this. And also we can say that we have finite number of pole and zeros. So but it will eventually one will be going from one to another. Okay, something like this. But we can never say whether they will be following the straight line or not. So maybe it will follow a path like this. Okay. So similarly, a path will be followed in the other way around as well. Okay. So, but how to know that? So for that, we are going to calculate the angle at which it will leave. Say for this particular case, the angle of departure from this pole will be from the always from the extension of the real axis. So this will be your angle of departure. And how it will be entering to this say for this pole, how it will be entering. So for that we need to know this angle, at which angle it is actually entering. So this angle here, this is called angle of arrival. So angle of departure is for the poles at which angle the complex from the complex pole the root will start, and for at which angle for the complex zeros the root locus will enter the zeros is called angle of arrival. Calculation is not that complicated. Calculation is relatively simpler because we know that the summation of all the angles, that is summation of zero angles minus summation of the pole angles, pole angles should be equal to odd multiple of twice k plus 1 into 180 degrees. Okay, so any arbitrary case, we have zeros, theta 1 plus theta 2 plus theta 3. These are the zeros. Okay, so and say we have poles, theta 4. Okay, so we have poles theta 4, theta 5, two poles, say arbitrarily. So it has to be equal to 180 degrees. And we are interested about this zero for which the angle of arrival we have to calculate. So you just keep this zero here, and the rest of the angle you take in the other side. So 180 degree minus theta 1 minus theta 3 plus theta 4 plus theta 5. So easily you can find out the angle of formula is same. So whenever we are taking a zero angle, we call this is angle of arrival, and whenever we take a say pole angle and we try to calculate that one, then we call it angle of departure. I think it will be more easier if we go straight into the example. So then you can easily see how it actually works. So go for example 8.6. Example 8.6. So kg of s. So I'm not writing, drawing the block diagram. So don't get confused in the exam if you see that block diagram is given. So I'm just figuring out what is kg of s, h of s. And I think you are also confused about the exam policy. We are also confused about it because of the whatever the rules or the regulations given to us. Actually, these give us wide spectrum of choices. We can take open book exam, we can take Viva, we can take assignments, and it is 40, 60, I think. 60 before meet and 40 after meet. So actually 128 marks we have to deal with. Okay, so I haven't yet figured out, most of us is also confused which one will be better for you, because at the same time we want two things. We don't want you to be deprived in terms of the grades. At the same time we want also have to be justified grades, like those of you who are actually working hard. If you get A plus, alhamdulillah, that's good. But if some of you who are not good doing the hard work, still they are getting A plus, that is actually injustice to those who are actually doing working hard. And also another factor is there. So the another fact is, if you get a good grade, you may think that it is good for you, but not necessarily. Not necessarily in a sense that whenever you have a good grade and you are going into the job field and you're seeing that your employee thinks that uh, you are an employee and your employer thinks that you know so many things, but this is not true, then he will be upset and your reputation and the reputation of the university will be also at stake. So that is why it's not always good to have good grade. It is always good to have the grade that actually judge you well. So in the so this is the closed loop and the transfer function that we need, kg of s, h of s. So we have two poles. Those are actually complex. So we're trying to figure out their location. So minus b plus minus b square, that is 4 minus 4ac. So 4 into 2. So divided by 2a. So basically minus 2 plus minus j2 divided by 2. So basically minus 1 plus minus j1. Okay, so first point is to figure out the location of the pole. So if you know the location of the pole, then it is easier for us to deal with. So say this is so this is what we have. Okay, so one pole as you have at -3 somewhere here. 1 0 you have here, and then two poles you have, one here, one here. Now we have to find out the angle of departure and angle of arrival for this particular zone. So let us go with the whole root locus. The first point is how many segments you should have. We should have 3 segments or 3 branches. So branches will be 3. How many infinite lines we'll have? Infinite lines will be 3 minus 1. So basically 2. So real axis intercept you have to calculate. So calculating the real axis intercept is also important. So sigma A is real axis intercept. So only the real axis component we are going to take. So poles is actually minus 3, minus 1, minus 1. So we are taking the real axis of this one, these two poles. Minus 2 divided by 3 minus 1. So basically 3 minus 1, that is 2 as well. Okay, so what we are going to get? Minus 3 by 2, and 3 minus 1.5. So this is your centroid or real axis intercept. Sometimes we call it centroid as well. So, and also the angles of the asymptote, that is theta A. Theta A is twice k plus 1 multiplied by pi divided by 3 minus 1, that is finite pole minus 0. So basically 3 minus 0 is 2, so twice k plus 1 into pi by 2. So k equal to 0 is giving you pi by 2 or 90 degrees, and k equal to 1 is giving you 3 pi by 2 or basically 270 degrees or minus 90 degrees. Okay, don't get confused about this. These are minus. Okay, so these are the guiding lines. So 1.5 is where you actually have the somewhere here. Okay, so let us try to draw the root locus. So let us also figure out the guiding lines that will actually help us to see what is actually happening. So guiding lines will be something like this. Okay, so now next thing is angle of arrival and the departure. So okay, so before going into that, real axis segment. So definitely only segment that will be on the root locus is this segment, and it will always start from the pole and it will go to the 0. So this is the segment, and this is your guiding line of 90 degrees and 270 degrees. So for this particular pole, because it is enough to calculate for only one pole because of the fact that the other pole, since it is complex conjugate, it is applying that formula, I think the formula 2, the symmetry formula. So it will actually have similar pattern as the other one. So actually calculating one is enough. So what you have to do, you have to calculate the angles. So you find out the angles from this as well as this one you draw. Okay, so this is your, don't forget the angle of this one. Angle of this one we are interested. So this is theta 1. This is your theta 2. This is your theta 3. And this is your theta 4, which we don't need to calculate because this is 90 degree. So our formula says that all the angles, theta 1, because of the fact that this is pole, this will be negative, theta 1 minus theta 2 plus theta 3, this is 0 angle, minus theta 4, it should be equal to odd multiple of 180 degrees. Or simply say 180 degree, because eventually it is within 360 degree. So whatever the angle you take, eventually it will be periodic. Okay, so now let us try to calculate the angles. So what will be the angle here? theta 1 we need to calculate, so we keep it as it is. So minus theta 1, and then minus theta 2 is basically tan inverse height is 1, and the base is actually 2. So tan inverse 1 by 2. Then you have theta 3, that is tan inverse 1 by 1. Height is always same. And for theta 4, we don't have to calculate it because of the fact that we can easily see it there in the straight line. So minus 90 degree should be equal to 180 degrees. So if you calculate them now, so basically it is minus theta 1 equal to minus tan inverse, that is minus 26.565 plus 45 degree, tan inverse 1 is 45 degree minus 90 degree equal to 180 degrees. So minus theta 1 will be equal to 251.565, and theta 1 is basically minus 251.565, or 360 degree minus 251.565 will eventually give you 108.435. Okay, so 108.435. So 108 approximately you can say. So we can make it 108. Okay. So approximately something like this will be a guiding light. Okay, so let us take another color, pick another color. So guiding line will be something like this, guiding the angle that which it will become. Okay. So as we know that this is angle of departure, but it can never actually cross the asymptotes. So we know that this is our angle 180 degree approximately. So from this real axis, this is our angle 180 degree point something. So 180 43, something like that. Okay, so what will happen? It will depart at this angle, then gradually it will become parallel to our path, the guiding line. So similar thing will be also happening here. So 180 degree it will start, then gradually it will eventually try to merge with the axis. Okay, so this is how you have to plot the angle of, you have to calculate the angle of departure in case of the complex poles, and angle of arrival in case of your if you have complex zeros. Okay, so calculation is very simple. The one that you want to figure out, give it as angle, and then apply the formula, that is summation of the zero angle minus the summation of the pole angle.